Okay, today we are going to solve a problem x to the power 6 is equal to x minus 1 to the power 6. And I am going to show three methods to solve this problem. Okay, first let's write this equation as a polynomial. X to the power 6 minus x minus 1 to the power 6 is equal to 0. Now, when we expand x minus 1 to the power 6, we see that x to the power 6 and x to the power 6 are going to cancel out. So we are left with a polynomial of degree 5. According to the basic theorem of algebra, for a polynomial of degree 5, we expect it to have 5 roots. That means that this equation right here, x to the power 6 minus x minus 1 to the power 6 equals 0, is going to have 5 solutions. Now, x to the power 6 minus x minus 1 to the power 6 is equal 0 is susceptible to the use of difference of two squares formula, which is a squared minus b squared is equal to a minus b times a plus b. So x to the power 6 we can write as x cubed squared minus x minus 1 cubed and then squared is equal 0. So we are going to have x to the power 3 minus x minus 1 to the power 3 times x to the power 3 plus x minus 1 to the power 3, which is then equal to 0. And this leaves us with two cases. X to the power 3 minus x minus 1 to the power 3 is equal to 0, or x to the power 3 plus x minus 1 to the power 3 is equal to 0. Now in this first case we are going to use the formula for difference of two cubes. It states that a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Well, that is going to transform our formula into x minus 1 times x squared plus x minus 1 plus x minus 1 squared, which is going to be equal to 0. Now for our second solution, we are going to use the sum of two cubes formula, which is a cubed plus b cubed, which is equal to a plus b, a squared minus ab plus b squared. And that is going to transform our formula into x plus x minus 1, x squared minus x minus 1 plus x minus 1 squared equal to 0. Well, we clearly see that in this part of the equation, x minus x plus 1 is just equal to 1. So we are left with x squared plus x squared minus x plus x squared minus 2x plus 1 being equal to 0. In this part right here, we are left with 2x minus 1 being equal to 0. And in third part, which is right here, we are left with x squared minus x squared plus x squared minus 2x plus 1 being equal to 0. X squared 1, 2, 3 times x squared minus 3x and plus 1 is equal to 0. We have that 2x is equal to 1, and in this part these two are going to cancel out, and we are left with x squared minus x plus 1 being equal to 0. So formula to solve this quadratic equation is x1 or 2 equal to minus b plus minus the square root of b squared minus 4ac over 2a, where a is equal 3, b is negative 3, and c is 1. That leaves us with x1 or 2 being equal to 3 plus or minus the square root of 9 minus 12 over 6, which is then equal to 3 plus or minus negative 3 over 6, which is 3 plus or minus square root of 3I over 6. And that is going to leave us with x1 being equal to 1/2 plus a square root of 3 over 6I, and solution x2 being equal to 1/2 minus a square root of 3 over 6I. Now in this second case we have that 2x is equal to 1, which basically leaves us with x3, a third solution of our equation, being equal to 1/2. And in this case right here we have x4, 5 is equal to, well, negative b plus or minus a square root of b squared minus 4ac over 2a, where a is equal 1, b is equal to negative 1, and c is equal to 1. And that leaves us with 1 plus or minus a square root of 1 minus 4 over 2a is 2. So this is 1 plus or minus negative 3. So that is a square root of 3I over 2, which means that x4 is equal to 1/2 plus a square root of 3 over 2I, and x5 is 1/2 minus a square root of 3 over 2I, which are all 5 solutions of our equation. Now a second method to solve x to the power 6 is equal to x minus 1 to the power 6. Well, basically we can take a sixth root to both sides of the equation, so we are left with sixth root of x to the power 6 and sixth root of x minus 1 to the power 6. This is an even root, so that basically leaves us with an absolute value of x being equal to absolute value of x minus 1. So in first case we have that x is larger or equal to 0 and that x minus 1 is larger or equal to 0, which means that x is larger or equal to 1. Basically, we are left with 0 and 1, and this interval right here from the first case includes 0, and this interval right here from the second case and includes number 1. Intersection of these two intervals is this one right here, so we are with x being from 1 to plus infinity. Now in this case we have that x is equal to x minus 1 when we get rid of the absolute value, and that basically leaves us with 0 being equal to negative 1, which is impossible. So this case right here offers no solutions. Now let's see what the second case is. Second case is for x larger or equal to 0 and x minus 1 being lower than 0. That makes x being lower than 1. Well, we are left with a case like this. So 0 is here, 1 is here, larger or equal, including the dot, and smaller without the dot. That basically makes x from the interval 0 to 1, when 0 belongs in an interval and 1 does not. Well, when we get rid of the absolute value, this case becomes x is equal to negative x minus 1, which makes it be equal minus x plus 1. 2x is equal to 1, and x is equal 1/2. 1/2 belongs in an interval from 0 to 1, so this is one solution of our problem. Now let's see what the third case is. That is for x smaller than 0 and x minus 1 larger or equal to 0, which makes x be larger or equal to 1. Basically smaller than 0 without 0 and larger or equal to 1. So this is with 1, and we see that intersection is an empty set. So this case offers no solutions. Now the fourth case is for x smaller than 0 and x minus 1 smaller than 0. X is smaller than 1, and basically that leaves us with this interval without 0, and this one without 1. Intersection is this one, so x belongs to from negative infinity to 0 without 0. And then our equation, when we get rid of the absolute value, becomes minus x is equal to minus x minus 1 minus x is equal to x plus 1 minus x plus 1, and that means that 0 is equal to 1, which is again impossible, so this case also leaves us with no solutions. So by this method we get that x is equal to 1/2 is one root of a polynomial x to the power 6 minus x minus 1 to the power 6. Now when we expand this, which I have already explained, x to the power 6 and x to the power 6 are going to cancel out, and we are left with a polynomial of degree 5, which has 5 roots, so we have 1. Now in order to find all other roots, the 4 ones that remain, we are going to take the polynomial x to the power 6 minus x minus 1 to the power 6, and we are going to basically write that polynomial as x minus 1/2 times another polynomial q of x. Basically p of x, which is equal to x to the power 6 minus x minus 1 to the power 6, is a polynomial of degree 5. When we take polynomial p of x and we divide it with x minus 1/2, we are going to get a polynomial q of x, and that means that q of x is a polynomial of degree 4. That means that q of x has 4 roots. So our problem becomes find roots of q of x, and so on. I find this method to be boring, so I'm not going to continue pursuing the solutions in this manner. Now, third method is one that I find the most fun of these methods. Basically, third method, and we are going to use complex analysis to solve this problem. X to the power 6 is equal to x minus 1 to the power 6. First, we are going to divide both sides with x minus 1 to the power 6, so we get x to the power 6 divided with x minus 1 to the power 6. This basically leaves us with 1. And we can divide like this only in the case that x minus 1 to the power 6 is different from 0. Division with 0 is not allowed. So x minus 1 to the power 6 is equal to 0 only if and only if x minus 1 is equal to 0, and that is equivalent to x being equal to 1. Now let's see if x equal 1 is a solution. So for x equal 1, we get that 1 to the power 6 is equal to 1 minus 1 to the power 6. Basically leaves us with 1 being equal to 0, which is impossible. So x equal 1 is not a solution. So this is where the fun begins. We are going to write x to the power 6 divided with x minus 1 to the power 6 as x divided by x minus 1 to the power 6, which is equal to 1. And then we are going to introduce the substitution as z being equal to x over x minus 1. And in that case, we get that z to the power 6 is equal to 1, where z is a complex number. Now all we have to do is find all 6 roots of number 1 in complex analysis. Now, when we are in complex analysis for z, which is a complex number, we can always use algebraic notation. And that means that we can write z as x plus iy, where x is a real part of number z, and y is an imaginary part of number z. Of course, x and y are both real numbers. What that means that when we put everything into a coordinate system, we have number z, we have its value x, and we have the value y. Well, that basically leaves us with this line right here, which has a length of module of z, which is a square root of x squared plus y squared, basically a Pythagoras theorem on this right triangle right here, and we are left with an angle phi, where phi is an angle arcus tangens of y over x. This angle phi is the main argument of a complex number z, and of course all other arguments are written in the form of phi plus 2kp, where k is a whole number. Now that leads us to a trigonometric notation of a complex number. Basically a trigonometric notation looks like this. We can take number z and write it in the form of module of z times a cosine of phi plus I sine of phi. And that leads us ultimately to an exponential notation. So exponential notation of a complex number, we are going to use Euler's formula. E to the power I phi is equal to cosine of phi plus I sine of phi. This is Euler's formula. Now we can write number z as module of z times e to the power I phi. Now for nth power of the number z, we always get module of z times e to the power I phi to the power n, and that leaves us with z to the power n times e to the power I n phi. And that basically leaves us with module of z to the power n times cosine of n phi plus I sine of n phi. Now what we can note here is that we in a real analysis had a power function which had a graph like this. Basically, the further you go with your argument on the x-axis, the bigger number you get. But in the complex analysis, while this also applies, you also get a rotation around the origin when you are working with power functions. Well, the question now becomes how to calculate an nth root of a complex number z. This is basically equal to z to the power of 1 over n, which is equal to module of z times a cosine of phi plus 2kp plus I sine of phi plus 2kp. And that entire thing on to the power of 1 over n. Let's say that zk is the number module of z times a cosine of phi plus 2kp plus I sine of phi plus 2kp. And that is for k, which is a whole number. The nth root of number zk becomes nth root of module of zk. Module of zk is basically equal to the module of z times a cosine of phi plus 2kp plus I sine of phi plus 2kp, which is then equal to nth root of module of z times cosine of phi plus 2kp divided by n plus I sine of phi plus 2kp divided by n. And this happens for number k, which is 0, 1, and so on to the n minus 1. Now let's calculate the sixth root of number 1. Basically, that means that z is equal to 1, and that makes module of z being equal to 1. And n is 6. Well, that means that number zk is equal to cosine of phi plus 2kp divided by 6 plus I sine of phi plus 2kp divided by 6. And k is 0, 1, all the way to 5. Now, when we look at a trigonometrical circle, basically number 1 is here on the x-axis, and its imaginary part is 0, so it makes the coordinates 0 on the y-axis. Well, that basically means that for z is equal 1, a real number of z is equal to 1 and imaginary part of z is equal to 0. Well, of course, that also means that phi, which is an argument of number z, is equal to 0. Well, that makes number zk be equal to cosine of 2kp divided by 6 plus I times sine of 2kp divided by 6. And of course, that is for k 0, 1 all the way to 5. So zk is equal to cosine of kp over 3 plus I times a sine of kp over 3, and that is for k 0, 1 all the way to 5. Now our number z0 becomes cosine of 0 plus I sine of 0, which is equal to 1 plus I times 0, which is equal to 1. Number z1 becomes cosine of pi over 3 plus I times sine of pi over 3, which is equal to 1/2 plus I times the square root of 3 over 2. z2 is equal to cosine of 2p over 3 plus I times sine 2 pi over 3, which is basically equal to negative 1/2 plus I times square root of 3 divided by 2. For z3, which is equal to cosine pi plus I sine pi, this is equal to negative 1 plus I times 0, which is equal to negative 1. Number z4 becomes cosine of 4p over 3 plus I sine of 4p over 3, which is equal to negative 1/2 plus I times negative square root of 3 over 2, which is then equal to negative 1/2 minus I times the square root of 3 over 2. And finally, z5 becomes a cosine of 5 pi over 3 plus I times sine 5 pi over 3, which is equal to 1/2 plus I times negative square root of 3 over 2, which is equal to 1/2 minus a square root of 3 over 2I. Well, since we used the substitution of z being equal to x over x minus 1, we have to find what x is. So x is equal to z times x minus 1, which makes x be equal to zx minus z. Basically, that means that x minus zx is equal to negative z, or x 1 minus z is equal to negative z, which makes x be equal to negative z over 1 minus z, and that makes x be equal to z over z minus 1. Now, area where our equation is defined is for all z which is different from 1. z0 was equal to 1, which doesn't belong in the area of definition, and that means that we have no solutions in this case. z1 was equal to 1/2 plus I square root of 3 over 2. Well, that basically makes x to be equal 1/2 plus I square root of 3 over 2 over 1/2 plus I square root of 3 over 2 minus 1, which is then equal to 1/2 plus I square root of 3 over 2 divided by negative 1/2 plus I square root of 3 over 2, which we can multiply by 1, so we don't change anything, but we are going to write that one as 1/2 plus I square root of 3 over 2 over 1/2 plus I square root of 3 over 2. And then we finally get 1/2 plus I square root of 3 over 2, that entire thing to the power 2, and we get negative 1/4 plus I squared 3/4, which is equal to 1/4 plus 2 times 1/2 times a square root of 3 over 2 times I plus I squared 3 over 4 over 1/4 negative minus 3/4, which is equal to negative. This is 1 basically, and we are left with 1/4 plus square root of 3 over 2I minus 3/4, which is then equal to negative 1/2 plus the square root of 3 over 2I, which is then equal to 1/2 minus the square root of 3 over 2I. And this was x5 solution from our first method. Now, in the case where z2 is equal to negative 1/2 plus I square root of 3 over 2, we are going to get that x is equal to z over z minus 1, which is then equal to negative 1/2 plus I square root of 3 over 2 over negative 1/2 plus I square root of 3 over 2 minus 1, which is then equal to negative 1/2 plus I square root of 3 over 2 over negative 3/2 plus I square root of 3 over 2. And of course we can do the same thing as before. Multiply with 3 over 2 plus I square root of 3 over 2 divided with 3 over 2 plus I square root of 3 over 2. This is basically equal to 1, so we don't change anything. This is then equal to negative 3/4 minus I square root of 3 over 4 plus I 3 square roots of 3 over 4 minus 3/4. Negative 9 over 4 plus I squared 3 over 4, which is then equal to negative 6 over 4 plus I 2 square roots of 3 over 4. Negative 9 over 4 minus negative 3 over 4, which is equal to negative 6 over 4 plus I 2 square roots of 3 over 4, and we have here minus 12 over 4, which is equal to negative 3 over 2 plus I square root of 3 over 2, and we have here negative 3. This is then equal to 1/2 minus I square root of 3 over 6, which was x2 solution in the first method. Now for z3 equal negative 1, we get that x is equal to z over z minus 1, which is equal to negative 1 over negative 1 minus 1, which is equal to negative 1 over negative 2, which is 1/2, and that was x3 in our first method. z4 is equal to negative 1/2 minus a square root of 3 over 2I. X is equal to z over z minus 1, and that is equal to negative 1/2 minus the square root of 3 over 2I over negative 1/2 minus the square root of 3 over 2I minus 1, which is equal to negative 1/2 minus the square root of 3 over 2I over minus 3 over 2 minus the square root of 3 over 2I, which is then equal to 1/2 plus a square root of 3 over 2I divided with 3 over 2 plus a square root of 3 over 2I times 3 over 2 minus the square root of 3 over 2I divided with 3 over 2 minus the square root of 3 over 2I, which is then equal to 3 over 4 minus the square root of 3 over 4I plus 3 square roots of 3 over 4I plus 3 over 4. 9 over 4 plus 3 over 4, and then this is equal to 6 over 4 plus 2 square roots of 3 over 4I divided with 3, which is equal to 3 divided by 2 times 3 plus 2 square roots of 3 divided by 4 times 3I, which is then equal to 1/2 plus a square root of 3 over 6I, which is x1 in our first method. For z5 equal 1/2 minus a square root of 3 over 2I, we get that x is equal to z over z minus 1, which is then equal to 1/2 minus the square root of 3 over 2I divided with 1/2 minus the square root of 3 over 2I minus 1, which is then equal to 1/2 minus the square root of 3 over 2I divided with minus 1/2 minus the square root of 3 over 2I. This is then equal to negative 1/2 minus the square root of 3 over 2I divided with 1/2 plus a square root of 3 over 2I. This is then equal to negative 1/2 minus the square root of 3 over 2I, 1/2 plus the square root of 3 over 2I, times 1/2 minus the square root of 3 over 2I divided with 1/2 minus the square root of 3 over 2I, which is then equal to negative 1/4 minus 2 times 1/2 times the square root of 3 over 2I plus 3/4 I squared divided with 1 over 4 minus 3 over 4I squared, and that is equal to negative 1/4 plus a square root of 3 over 2I plus 3/4, which is equal to 1/2 plus a square root of 3 over 2I, which is equal to x4 in our first method. If you have watched this video so far, I suspect that you have found it to be somewhat useful. I am looking forward to reading your comments and suggestions. Please subscribe to the channel if you want to see more problems like this getting solved. I suggest that you watch my next video, which I have linked here.